So I really enjoyed this chapter. I know the last chapter I mentioned that energy was very tangible. You could see and understand things. And it's very similar with this chapter as well. The concept of momentum, even impulse. You don't know what that word means maybe. Maybe some of you do. But physically or in terms of physics, what does impulse mean? It's extremely relatable to everyday activity. I mean, things that you do all the time. I have an orange for a reason. I'm not just carrying an orange around. So if any of you before have ever had, how many people grew up in the suburbs? Suburbs. Did you ever have a block party? Do you know what block parties are? When I was a kid, we had block parties all the time. And a block party was pretty much, you close down the block, right? They put the fire things up so people couldn't drive on the block. And the entire day was a party. And like your family would come out when you were kids, obviously. Like adults would have a good time. Kids would love, like it was just fun, right? So every year we would have egg toss competitions. Did you ever have this? Like a water balloon or egg toss? Or the spoon one is the egg run. But then there's the actual egg toss. So the little kids would have a water balloon toss. And the winning group, every time you caught the ball, the water balloon successfully back up. The winning group of the kids group got to go against the adults. And the adults had the egg toss if you're older, because they didn't want to get egg all over the place. And the egg toss was epic because you would start by going across the street, but eventually groups would get so good that you had to turn this way. And you'd be going, like, no joke, like 200 feet with an egg toss down the block. I'm not kidding. And I talk about my family all the time. I have 3 brothers, and we'd always win it. And my dad was amazing at it. He was the best. I mean, he was our baseball coach, and he always talked about what's called soft hands. And in baseball, if you have soft hands, what does it mean if you have soft hands? What am I doing? You're able to do what with the ball very easily?
When you catch it, you cradle it.
Yeah, you cradle and field the ball very nicely, very, very smoothly. A player in the pros, you would see like a shortstop always has soft hands. You see any balls hit to him, he just absorbs it into his body, no matter where it goes. That whole concept of soft hands in baseball and the egg toss, that's what momentum and impulse really is. So if you think about, I gave the example with an orange last class, but then I thought about the egg toss also. This orange, it's a little bit dented, it got messed up in my bag a little bit, but it's still pretty good. But if I were to toss it to somebody, and he were to catch it just randomly, if you were to catch it just in your hand as it's moving, give it a toss back. So if I went like that, see what I just did? Did you hear the sound? I probably put a lot of dent on the side of this right now, right? And later it's going to be a little bit like all gross, but it'll still be able to eat. Now, if instead of catching it when Trooper threw it back, I did that on purpose. If instead of doing that, I had done this like Trooper did, when he caught it, he went like this. You saw his hands just go back automatically. What you're doing is God bless you, you're increasing the time that the orange is contacting your hand before it slows down. So earlier, ready, think, splat. It's like maybe 1/10 of a second, and it goes from full velocity to no velocity. Now, when you soft hands and you cradle something, as you're about to catch it, it's got full velocity, and you do this, and at the end, it's got no velocity. But the entire time that your body is absorbing the impact, you're increasing what's called the time period of contact. Why do you do that? What does it do? And use physics terms. It's tough to answer this. You can use common sense, but try to use physics terms. What are you physically doing by increasing the amount of time instead of going smack and like hearing it? Travis.
It slows down the decrease in velocity.
Yeah. Very good. It slows down the rate at which the velocity is decreasing. What was defined as the rate at which velocity decreases or increases? When velocity changes? Acceleration. So by definition, what Travers said is you're really just reducing the amount of acceleration. And if you remember F equals ma, acceleration is directly related to the force. So by increasing the time, I'm putting no force on the orange. And think about it logically now. Use logic, right? When he threw it back to me, it hit my hand, and it stopped instantly. I put a dent in the side of it for sure, like at least a good welt in the side. But as soon as you do this, it's not going to happen. The egg toss is the exact same thing. So those block parties, the groups that always won were the groups that you saw, people, men or women, both, because it was both, softball and baseball, right? Doing this every time, doing this, like catching the block. And it was usually somebody who had played sports before, or baseball before, because they understand the concept of soft hands. But really, what is it? It's physics. That's all it is. Now, the idea of the force and the time period, that's where impulse comes to play a role. Momentum is it is a function of an object's velocity and mass. The mass of the object, in this case, is never going to change. Right? We do have problems. If you go into AP Physics next year, you'll learn about variable masses, like a rocket. As a rocket propels itself into space, it burns fuel. So its mass decreases, actually. It's got this big chamber full of fuel, and it's got to burn fuel to escape the atmosphere, or the pull of gravity on the Earth. So as a result, it burns a lot of fuel, decreasing its mass. This mass is not changing. So when Trooper threw it back to me, it had a velocity, and I suddenly caught it like this, or tried to catch it, and suddenly the velocity was 0. So the change was in velocity. So we're going to see momentum here is related to impulse, because the change of the actual momentum of the object is what the impulse is absorbing. It's absorbing all that momentum. How many people have, let me go through several examples. There's a couple I can think of. How many of you have either jumped in a pool in the summer, participated in some sort of gymnastics, or something where you have to absorb shock upon impact? Dirt biking I think about a lot. Dirt biking, when you land, you don't land rigidly. If you jump as a gymnast, you don't land with your legs locked. Have you ever tried that before? It actually physically hurts. Try to lock your knees. My knees are locked right now. You never do this in any sort of athletics. And imagine jumping and landing. You hear how annoying that loud that was? I actually felt like vibrations in my mouth. That's how, because the force you feel translates through your body. But the minute you jump and you land softly like that, how many of you before, come on, be honest, have tiptoed in after curfew, right? And what are you doing? You're not going like this up the stairs. That's a lot of impulse, because the time at which you're hitting the stairs is quick. Instead, you do this. You're literally creeping along the house. Because what's happening? The force that you're applying every step is slowly, under a long time period, being absorbed by the ground. So you're not hearing the sound as a result. It's impulse. That's what it is. You dive in a pool, you jump in a pool, belly flop versus cannonball. Belly flop, all of that force is at one instant, right? Your body smacks the water at one instant. But when you do cannonball, the weight of your body over time goes into the water. First, your legs, then the rest of your body. There's a couple other reasons for that, but the idea of impulse there. Gymnastics, again, you absorb the shock of the knees. Dirt biking, racing like that, horseback riding, anything where you're absorbing shock as you go through the motion, driving a car, NASCAR racers, those have shock absorbers. That's why you have airbags in a car. The airbag is not really a cushion, it's an impulse absorber. That's what it is. Yes, if you just jump down flights of stairs. Oh, how about, you're going to add one or not?
Oh, well, in boxing,
Boxing?
they teach you that if you're gonna, if you have to get punched in the face, you can either take the whole blow here short.
Well, what do you do?
Or you roll with it.
You move your face
roll
like that.
back.
That makes sense. You hear what he's talking about, boxing? If your head stays where it is and you get hit, versus going like this and naturally rolling your body off of it on purpose. Marines, Navy SEALs, those kinds of guys, any special forces that parachute to areas, they don't land in a running land. They land and do a quick roll. They actually do. They'll land, and to absorb the shock of the impact quietly, they'll do a somersault forward and then get right up. Some of you knew Julian Matisse. He was into parkour big time. And later in the year, he loved parkour. You've seen these videos, I'm sure. And later in the year in physics, you're going to do a project where you have to do a video project. And you have to talk about physics and everyday life and record you and a group members doing these things around the city and stuff. It's a fun project. I like it. He and James Hill did their whole thing on parkour because it's all physics. Every time they would jump from one location to another, their inertia, and then upon landing, ever see somebody that is into parkour land off a jump, they naturally roll every time. And they absorb the shock by increasing the time period of contact. Okay, so this entire lesson here, 7, 1, and 2, I combine these two sections, but this entire lesson is about the concept of mass, velocity, time, and force. The mass and velocity, and I'm going to go into this in a minute, have to do with your momentum. The force felt and the time have to do with impulse. And we'll show how those things are related in a minute. All right, so let's get started with that. So first, similarly to kinetic energy, or similar to kinetic energy, momentum is a function of the same two parameters, mass and velocity. It's different though. This is the formula. What was kinetic energy again? Formula? 1/2 mv squared. This is just mv. It's a lot easier actually. See that? Mass times velocity. That gives you momentum. There is no simplified unit for this. Like in energy, it was joules, right? For kinetic energy, it was all in joules. Here, there is no simplified unit. The unit of mass is kilogram. The unit of velocity is meter per second. This is kilogram meter per second. There is no simplified unit. It gets annoying. I apologize, but it's just the way it is. It's called P for a reason. The letter P for momentum, because some students later in the year confuse it with power, which we kind of skipped in section 6.4. There's 2 P's in a row actually there. The lowercase letter P stands for actually what's called progress. So Newton and Leibniz were the 2 leading mathematicians, physicists, calculus founders really. And Newton came up with this idea and said it has to do with, an object in its state of motion and wanting to maintain motion and inertia. And he talked about that for a little while. He called it the quantity, really, Newton. But Leibniz said it's really the progress that an object makes. If an object has mass and it has velocity in a given direction, it will move. It'll make progress. So he called it progress. That's where the letter P comes from. It doesn't matter, but just know that P stands for momentum when it's lowercase. Capital P is power. Okay, capital P will be power soon. Anyhow, so momentum equals mass times velocity. So if the momentum of an object is not changing, you can see that if you increase the mass to keep the momentum the same, you got to decrease the velocity. Now, if we think about a very simple example, we'll see in example 1 with a bullet and a bowling ball. But think about a realistic one. I know there's a lot of just sports fans in general, and it's an easy thing to relate to with physics, it really is. For 2 football players running into each other. This is the prime example. So, and this has happened before where like a linebacker goes to tackle the running back, and imagine there's no yards after contact. They contact, and the guy goes right down. Okay, so the linebacker goes to tackle the running back, maybe hits him low, and he drives him right to the ground instantly. That would be a perfect balance of momentum where the linebacker has most likely more mass, but he's not running very fast. The running back, who's smaller, has less mass, but he's running really fast with high velocity. If those 2 things combine and hit together, just like Newton's laws, when forces are balanced, you're in a state of what? Equilibrium. This is the same idea. This is like a balance of momentum here. The momentum of the running back and the momentum of the linebacker are equal and opposite of each other. So when they hit together, what do? They just stop. If one of them had more momentum than the other, he or she would plow through or run through the other person. There's a lot more to tackling than just momentum, but that's a simple example to understand there. So what I'd like to do now is to show you a quick derivation of how this is related to impulse. You don't need to necessarily write every single thing I'm writing at this point. You can just watch for a little, but the very end of this, you should definitely box in, like we did with the work kinetic energy theorem. I went through the whole where it comes from and everything, but you needed to know the actual theorem at the end. Here we're going to do the same thing. So we're going to derive what's called the momentum impulse theory. So let's start by dividing both sides by time. Start by dividing both sides by time. What I do to one side, I have to do to the other, right? So I can divide both sides by time. It's like saying divide both sides by 2. You can always do the same thing to both sides. Next. There's something in calculus called the differential, and it means change in calculus. And you're allowed to apply these to each side of the equation. You can look at the change in an object's value. Now, what do we know as change in physics? What symbol do we use for change? Delta, very good. So apply a delta symbol. Apply a delta symbol to P real quick. And if I take the delta of one side, I know this isn't mathematically correct the way I'm saying it. But if I take the delta, the change of one side, what do I have to do to the other side? I have to also apply change. But look at your numerators, guys. What did I say earlier? Can mass change or can velocity change? Which one are we going to be focusing on? Velocity changing. Mass can change, but as soon as mass starts to change, you have to use what are called differentials, and you have to use calculus to actually solve these problems. So we're going to assume that mass is consistent and that the change is going to be involved in the velocity. So I can do that to both sides. Again, I did it to one side, I do it to the other. Can somebody tell me what I can replace this with, what I've circled here? What can I replace that with? What's the definition of that? I can easily replace that with another term, another variable, another parameter is equal to that. Gus? It is acceleration. Very good. So let's, on the next line, write down this. So I'm simply replacing delta v over t, because the change in velocity over time is what acceleration is defined as. And what else? Come on, use your intuition. What substitution should I make next? It should jump out at you. You should see it. You should see it. Come on. You saw delta V over t was acceleration. Look for something else you can substitute for. ma. What's ma equal to, everybody? F. F equals ma. So let's go ahead and write that. And if you recall from class, it was F net, right? F net equals ma. If you want to write net, you can. Net just means the overall force. For any of these momentum impulse problems, we're going to be using the overall force on the object. So if I want to solve for my delta P, I get F times T. And this here is called the momentum impulse theory. Here's your impulse. That's what impulse is defined as. F times T is impulse. And this is your change in momentum. This is the momentum impulse theory. And remember, if you want to write a note to yourself, F, I don't write it in the formula because it gets annoying, but F is really F net. It's the overall force acting on that object. So take this concept, look at it real quick, and make sense of the egg toss again. So, all right, we got two eggs coming in. We got two groups, they're both tossing, it's the final group, right? One group tosses the egg, the other group tosses the egg. They both toss the egg with the same velocity. That has to be stated, or else it's not going to make sense. So both groups toss with the same velocity. One group holds the hand up, smacks into his hand, stops instantly, breaks everywhere. Another group catches it, eventually stops, it doesn't break. Either way, they started with the same velocity. Eggs have the same mass. They ended with the same velocity. What's the velocity at the end? 0, it stops. So it starts with the same velocity, ends with the same velocity. Both groups are throwing the same egg, same mass. As a result, this is not changing between the groups. Both groups are changing the momentum of the egg by the same amount. But what's changing is this. One group has a really small time period. So this is a very small number. As a result, what kind of a number will this be? A very large number. So you put up your hand, hit your hand, egg splatters. A lot of force. Now you do this, you take a lot of time to catch it, making this a high number, which would do what to this number as a result? Lower it. Low force. The egg won't break. You will not exceed the yield point of the egg structure. Yeah?
So like, if you just boiled an egg and then like did a little switcheroo.
Yeah, I mean, yeah, you definitely could. But usually I know. So people have tried to do that on the fourth quarter project. It's called the egg drop. By the way, this is like your theory for the fourth quarter project here. For the egg drop, students have tried to bring in their own egg. I just provide the eggs. That's what they did at the company. Yeah, right? I mean, I guess if you had it in your pocket and you just like did a quick switcheroo.
Like a joke, like in your jacket.
All right, I can see that.
Like you catch it and
you're like, oh!
No, you just get it right here.
It'll never break, yeah.
There you go.
Gus, I like your thinking, cheater. Yeah.
Are these indirect variables?
So yeah, F and T are indirectly related to each other. Look at F and T. Assuming delta P is held constant, right? This is not changing. Pick a number for delta P and you can prove this mathematically. Pick 24. It works out very nicely because it's divisible by many things. Let's say that the change in momentum of this object is 24 kilogram meters per second, whatever it is. And we're trying to figure out the force felt if you catch it in 1/10 of a second. Divide both sides by 0.1, you're going to get 240 newtons. So that's the force felt if you catch it really quick, after 1/10 of a second. Now the other group is doing the same thing, but the other group is taking almost 2 seconds to catch it. What's the force felt instead? 12. Look at the difference. So the group that catches it really quick in only 1/10 of a second, in 0.1 seconds, this group that just puts up his hand and smacks into it in 0.1 seconds, the egg will feel a force of 240 newtons. But the other group, where they cradle it and catch it for 2 seconds, it only feels a force of 12 newtons. A hugely significant change in factor. Okay, we're talking about here 20 times more force. Because the time period, how much bigger is 2 divided by 0.1? 2 is 20 times more time than 0.1. So the force felt is 20 times greater. Those are not coincidences at all. Is that clear? See what I'm saying there? The force felt is 20 times greater in the first scenario than the second, because the time it takes in the second scenario is 20 times greater than it was in the first. Those things are indirectly related. You increase time by a factor of 20, it decreases force by a factor of 20. If you double the time it takes to slow something down, you have the force it feels. If you triple the time it takes, you third the force. You cut the force in 1/3, or cut it in 3. All right? Let's look at some examples of this so you guys can see this now. So the first example we've got, what velocity must a bullet have if its mass is only 4 grams in order to have the same momentum as a bowling ball with a mass of 6 kilograms that has a velocity of 8 meters per second? So this is very, very similar to section 6.2 with the kinetic energy, and there was a bouncy ball. I used an example with a bouncy ball and then another object, another ball. I think it was also a bowling ball. The idea I want you to think about here, is that, sure, you could find the momentum of the bowling ball first and then set it equal to the bullet, and that takes several steps. Or you could just say, you know what? If the momenta, plural momentum, if the momenta are supposed to be the same, then the momentum of object 1 equals the momentum of object 2. And the formula for momentum from the previous slide is mv. So this is mv, and this is mv. So that's all you got in this problem. That's all you need to really do. The mass of the bullet. What's the mass of the bullet? What are we going to write down for the mass of the bullet? Be careful. You got to convert it because the other one's in kilograms, right? Do you remember that one? Other way. Very good. There's our mass. That's the mass of a bullet. 4 grams, 0.004. The mass of a bowling ball is 6 kilograms. And its velocity in this problem is 8 meters every second. So we've got, again, the bullet on the left as object 1, the bowling ball on the right as object 2. What will your answer for V1 be with respect to V2? I'm not asking for a number, I'm asking for a general relative term. V1 will be blank compared to V2. Much larger. Why? Why is it heavier or larger? Why is it greater? What's the reasoning?
Because 6 times 8 is going to be like a bigger number and 0.04 is such a small number. You need like something really big
To balance it out. Yeah, look, your mass is so much lower than the other mass was, right? So for these to have the same momentum, it's like the linebacker and the running back. The running back can run as fast as he wants, but because his mass is so small, he might not be able to keep up with the linebacker in momentum. But because this mass is so small, V1 has to be extremely large. What do you get? V1? What do you get? 12,000. And yes, meters per second.
Notice that Travis always has.
He has all the calculations.
Yeah, Travis is quick. Well, see, I rely on people that I see have calculators out, and he does, Tiana does, a couple others always have maps. I always look for the calculators when I put it on people for these. You'll notice that. I don't. If you have your iPad, I usually don't call on you for numbers. Thank you, Travis, by the way. And thanks, guys, for pointing it out, because we all need to know that, too. So V1 in this case, V1 is so much greater. How much greater is it, is the question, actually. Let's think about this. Take your calculators. Please take... No, Travis, you can't do this one. Sorry, you just can't. You can't do this one for us. Take 6. Take 6 and divide it by 0.004. Take 6 and divide it by 0.004. What do you get? 1,500. So the bowling ball is 1,500 times larger in mass than the bullet, while the velocity of the bullet is 1,500 times larger than the velocity of the bowling ball. Try it. 12,000 divided by 8. You'll also get 1,500. So again, the ratios appear for a reason. They're not arbitrary. They're not randomly appearing. Questions? I posed a follow-up in the other class, but I might run out of time, so I'm going to wait on that follow-up. The follow-up just had to do with what would happen at the end. Think about that. What do you think would happen if this scenario were to, if these two objects actually came together? We'll get back to that if we have time. Example 2. Now, the previous example was just about momentum. Let's start looking at momentum impulse. The reason I know it's going to be impulse, I'm seeing what looks like time. As soon as I see time in these problems, I'm thinking that's t. It's probably momentum impulse theory. Delta p equals ft. So we've got a mass of 1,500 kilograms. The car is moving with a velocity of 20 meters per second, and suddenly it collides with a tree. It collides with a tree and it comes to rest. It takes 2 seconds for the front end of that car to kind of cave in, and the car comes to rest after 2 seconds of contact time. Find the force exerted on the car during the collision. So a positive velocity means I'm moving this way, right? So I'm the car, I hit the tree, I stop. How can the tree stop me? By doing what? Think about physics. Use physics terms. I'm going this way. The only way the tree can stop me is by doing what physically? What does it have to actually do? Gus?
Has a high mass.
Sure, that's definitely true. It has to have a high mass.
Exert a greater force on you.
Which way?
Back end.
Yeah, back at you. Very good. It has to exert a force. Very good. And the force that can combat what you're currently exhibiting in that direction. But it has to exert a force against you. So what kind of an answer should we get for F? Yeah, because what kind of velocity did you have in this problem? What kind of velocity did you have? To start, what kind of velocity? It says 20 meters per second east. Which way is east? Not in the city, but imagine right or left? Right. West is left. You mix them up. East is to the right, west is to the left. So east is considered positive. So this car starts with a positive velocity of 20, comes to rest after hitting the tree. It takes 2 seconds. Its mass is 1,500 kgs. And our goal is to figure out what's the force. See how quickly I just did that? Because I analyzed the problem and I thought about what was physically happening. I used my units also. Notice? A lot of you are getting really good at this now, I picked up on. Use your units. On the last test, the units were huge. I can't go into detail. Okay, a couple of them take it still. But the units were huge on the last test. It really helps a lot to identify what units in the problem so you know what variables you're going to use. Okay, so this is the analysis or the setup we've got. What's the formula I'm going to use? I can't just use P equals mv anymore, obviously. There's a lot going on here. I'm trying to find force. What formula had force in it that we just looked at a little while ago? F equals ma works. You actually could use F equals ma here, believe it or not, because you could find A. Look, change in velocity over time, and you could use F equals ma. It would be 2 formulas you'd have to use though to do that. So I'm going to have you use only one formula. Yeah, delta P, either over T equals F or equals F times T. It doesn't matter which way you represent it. But again, I want to point this out. What Tiana said is a really important thing here. Notice, you've got a change in velocity over time. So what could you easily calculate from that if you wanted to? Acceleration. And if you know acceleration and you know mass, you can find F. So you could do this in 2 steps by finding acceleration first and then use F equals ma to find the force. So I want you to see this because on the midterm, it's up to you to choose which way you want to approach this problem. You can use momentum impulse theory and it's only 1 step, or find acceleration and use F equals ma. It's 2 steps, but they're 2 pretty short steps. So either way is absolutely acceptable. It doesn't matter. Just like on the last test, I mentioned that you guys used energy. You could have solved those problems, some of them on the last test, using projectile motion. On that test, I wanted you to use energy. But in the midterm, use whatever method's easier. Either way, you get the same answer. Okay? So delta P, what does delta mean? Change. Final minus initial. Okay? Final minus initial. I slow down because some people put initial minus final sometimes. Final minus initial. The definition of momentum, P, is just mv. So I'm going to replace it with mv, but because the I is final or initial, I'm going to specify with a subscript. Again, this is the momentum at the end, this is the momentum in the beginning. What's the momentum of this object after it's already collided with the tree? After it's collided with the tree, what's its momentum got to be? It hits the tree, it stops, what's the momentum? 0. So we know that the final, because this right here, look, final velocity was 0, right? That whole thing goes to 0. which gives you the following. Now, a lot of you have been doing really well in the last few chapters. I really challenge you to start solving algebraically if you find yourself in that case. If you're struggling a little bit with the math still, honestly, by all means, plug in numbers here. It doesn't matter. No way is it doesn't matter which way you do it in this class. You'll get the same amount of points. I'm trying to maybe push a few of you that might want to take AP Physics next year and say, you know what? Solve for this generically. So solving for f is really simple here. What do you get when you solve for f? Get f alone. F equals what? In variables, I mean. Yeah, negative MVI and just divide by t. All you're doing is getting rid of t. T is multiplying f, so divide both sides by t. And then plug in numbers. That would be my encouragement. But again, it doesn't matter. You can plug in at this stage right here. Plug in mass, plug in a 0, plug in mass, plug in 20, plug in the time of 2, and solve for f. Or plug in right here. Or solve generically and plug in here. It doesn't matter. Notice what sign you have here? Negative. Why is there a negative sign there? What kind of a force did we say we were going to have? Yeah. You're going to have a force that resists motion. Motion is positive. The force must be negative. Negative 1,500 kgs times the velocity of 20 meters per second all over 2 seconds. And if I didn't know what my units were, I could check here. I'm going to end up with kilograms times meters per second squared, which is what a Newton is defined as, which is why my answer for force is given in newtons. How many newtons is it? What do we end up getting? How many newtons do we get for this problem? Bernadette, what do we got? Negative 15,000 newtons. Agreed? I agree. And negative 15,000 newtons. Again, to point out that Tiana was absolutely right. You could use F equals ma here, and you could solve it that way also. And I encourage you to practice that. Try that on your own. When you're reviewing for midterm, that'd be a good way to look at other problems. Try approaching them more than one way. Okay, we got one more for today. One more. We're going to finish this one. I know the bell might ring, but we're going to finish this before we leave. I'm going to have you watch example 4 again. Watch example 4 tonight. Start the homework. We'll do example 5 on Thursday. The homework is due Friday morning, 8 a.m. Okay, you guys there's no class on Friday, right? So get it done Thursday night. Don't think you can submit it during the day on Friday. Google Drive, just do it. Friday's assembly, Christmas assembly.
There's no way we can see Friday.
If you see me on Friday, that's fine, yeah. But honestly, with Friday assembly, it might be tough. Put it in my mailbox at least then or something. Yeah, that's fine. So a soccer ball is kicked. It's moving to the right. What kind of velocity? To the right? Positive. It bounces off a wall. And we're trying to figure out what's the velocity after it hits the wall. What kind of answer are we going to get? Negative again. The velocity, though, this time. What is given instead this time? We're not finding it this time like we did last time. It's given. What's given? The force is given. Now, if I hit the wall, which way does the wall hit again? It hits back. So what kind of a force should I put?
Positive.
My velocity is positive. My velocity is positive, so the force has to be negative. It's got to be the other way. Remember, when I kick the soccer, it's okay. I'm glad some of you are right sometimes. When you kick the soccer ball into the wall and it rebounds off the wall pushes back. So look at this problem. The hardest part is to recognize that this is actually given as negative 42.5. The wall exerts a force of 42.5 newtons on the ball for a time period of 0.2 seconds. The initial velocity of the ball was 9 meters per second. Its mass is 0.5 kilogram. And our goal is to find the velocity after it impacts the wall. It's the same exact problem. It's really the same problem. Instead of coming to rest, it's rebounding. So you're going to find VF instead of VF being 0. But the analysis is identical. You start with everything the same way. You start with, again, delta P equals Ft. Or in this case, you could find the acceleration using F equals ma, and then set the acceleration equal to change in velocity over time to find that final velocity. So you could use Newton's law, F equals ma, to give you acceleration, and then say A equals Vf minus Vi over t, and solve for Vf. Give me another minute. Yeah.
Would acceleration be equal to velocity as well?
No, remember acceleration is either the change in velocity over time or use F equals ma and solve for acceleration there. So delta P, just watch me for a second. You can take this down later or now, whichever. Okay, so this, by the way, notice, I'll point to it real quick. This is something that maybe you could start with every time if you get comfortable. There's no need to start with this formula. Take a look up, please. You don't have to start with this formula every time. Maybe jump right to the third formula every time when you do this, because it's always going to be the same formula for momentum impulse theory. Okay, start with that formula if you'd like to. Now, you can plug in everywhere, or you can solve for VF. You can solve for VF. I would move this whole term over and then divide by M. So this is what I get if I move the whole term over by adding MVI, because MVI is currently subtracting from this. I'm going to add it over. So I move it over like that. And then I divide by mass. Okay, that would be my final solution. Or again, I'll point out that at this point in time, right here, you could have plugged in. If you plug in everything you know at this point, you know mass, you know VI, you know F, you know T, you'd have to solve for VF. Okay, it's the same thing I did here algebraically, solving for VF. The answer turns out to be -8. It's negative because it's rebounding off the wall, units of meters per second. Okay, I'll leave it to you to practice. Either plug in here and solve for VF, or solve for it here and plug in. Okay, remember the stuff you got to do. Watch example 4. If you don't watch example 4, example 5 will not make sense. And we're doing that on Thursday, so watch it. On Thursday, we'll do example 5, and then you got the roller coasters the rest of the period. Okay? Please watch this tonight and start the homework. It is due on Friday at 8 a.m.
The M just cancels out, so can I do...
It doesn't cancel out, though. If you look, it cancels out here. Take a look. Those M's would cancel,
that's
right?
What I mean. So could I do F times T plus VI?
But F times T has to be over M. See, M has to be divided to both, right?
Okay.
So you could write FT over M plus VI. See what I'm saying? Write this as one quantity, FT over M, plus, and instead of writing MV over M, just write V.
Okay.
Okay?
Yep.